This video cast is about the concept of pH. This first little bit that I'm going to talk about is kind of the derivation, how we got the pH scale. So if it goes a little bit over your head, it's okay, but this is how it all came to be. So aqueous solutions and the concept of pH. It started with water. Since most of the solutions that we deal with in and outside of chemistry in our everyday life tend to be water-based solutions, we have to look at water and how we treat the acidity or basicity of anything. Water provides both hydronium and hydroxide ions. And the reason for that is because it will self-ionize. It is a weak electrolyte. So what happens is you get two water molecules together. One water molecule will pull the hydrogen off of the other one. And so you end up with hydronium and hydroxide ions. And then, of course, this is a double-headed arrow. So the hydroxide says, hey, give me back my hydrogen. And then you end up with two water molecules again. It ends up on this side. And then it just goes back and forth, back and forth, back and forth as we go. Now, as we talk about this, we're going to be saying hydronium and hydroxide a whole lot. Those two words are very, very similar and start with the first 5 letters. They are the same. So you need to make sure you read all the way to the end of the words to distinguish the difference. We need to associate hydronium with our acids and hydroxide with our bases, as we talked about in the last video cast with defining acids and bases. So hydronium's our acid stuff and hydroxide is our base stuff. And water will give us both. So when they were testing water, they used some conductivity measurements and found that the concentration of hydronium ions and hydroxide ions in pure water are each 1 × 10⁻⁷ moles per liter, which is molarity. Now that is at 25 degrees C. It does change as temperature changes. When you see those square brackets, and I read it as concentration, and that's how it will be, and you'll see this a whole lot as we go through the rest of chemistry. Square brackets around something mean the concentration of whatever's inside of it in molarity. In this case, I have the hydronium ion in square brackets. So that means it is the hydronium ion concentration in moles per liter, which is the same thing as molarity, represented by that big M. All right, so we're going to be using molarity quite a bit in this chapter. So as they did this, they came up with a constant, and in chemistry we start to use K's as our constant, and it's Kw because we're measuring water, and that's what the W stands for. So if you take the concentration of hydronium and hydroxide, each of which are only 1 × 10⁻⁷, we find that constant is 1 × 10⁻14 molarity squared. We use that for water-based solutions, and if we have the hydroxide or hydronium ion of concentration of anything, we can use it to find the other one. So this equation here that's in the box is going to be our working definition. We're going to use it a lot. If we know one, either hydronium or hydroxide, we can use this equation to find the other one. And this is given in your reference tables. Now again, ionization of water does increase as temperature increases. So that number was at 25 degrees C, which is room temperature for chemistry. So here's how we're going to use this. Hydronium ion concentration of a solution is 2.5 × 10⁻⁶. What's the hydroxide ion concentration? Because these words are very, very similar, we tend to read them very fast. Hydronium, H3O+, is what we have here, and we're looking for hydroxide ion concentration. The easiest way to go between these two is using this equation right here. So that's what we're going to do. I'm going to take this equation and I'm going to solve it for hydroxide. So if I want hydroxide ion concentration to be by itself, I have to divide both sides by the hydronium ion concentration. So it ends up being hydroxide ion concentration is equal to 1 × 10⁻⁴ molarity squared. Now that squared is just for the molarity. It does not go with the number, just the units. And then I'm going to divide that by my hydronium ion concentration. Now, I'm just going to plug these in, or the number in that they gave us in the problem. They gave us our hydronium ion concentration, so that's just going to go in right here. So it's going to be 1 × 10⁻⁴ molarity squared divided by that 2.5 times 10 to the negative 6 molar. When you divide those, you find that your hydroxide ion concentration is 4.0. We want to deal with 2 sig figs since that was given in the problem, times 10 to the negative 9. Molarity cancels with one of these, so I'm just still left with molarity, and that makes sense because if it's square brackets equals, the units are in molarity. So that's just a really quick way to work with this equation and go from hydronium to hydroxide or hydroxide to hydronium. It's always 1 times 10 to the negative 14 divided by the one they give you in the problem will give you the one that you're looking for. All right. The next thing we'll have to do is talk about classify this solution as neutral, acidic, or basic. So, if our hydronium concentration is equal to our hydroxide concentration, that means our acid stuff is equal to our base stuff, then we end up with a neutral solution. If our hydronium ion concentration is bigger than my hydroxide ion concentration, I have more acid stuff than base stuff, then it is acidic. And if my hydroxide ion concentration is greater than my hydronium ion concentration, my base stuff is greater than my acid stuff, the solution then is basic. So if we look back at the problem that we just worked, and this is our hydronium ion concentration, and this is our hydroxide ion concentration. We're going to compare these two numbers to decide whether the solution is acidic, basic, or neutral. Now, you want to pay attention to these exponents because here's where it gets a little tricky. Remember, times 10 to a negative number means we have to move, this is a tiny number, and we got to move the decimal 9 places in that direction. So that's going to make that a very small number. And it's going to end up, our hydroxide is smaller than this number right here for hydronium because this decimal only has to be moved 6 places. So our hydronium ion concentration is greater than my hydroxide ion concentration because 2.5 times 10 to the negative 6 is greater than 4 times 10 to the negative 9. So the solution is acidic. The next problem I have is very similar to this one, so I wanted to see if you could try it. You can pause this video cast and see if you can figure out the hydronium ion concentration and whether the solution is acidic, basic, or neutral. Okay, in solving this one, we have our hydroxide ion concentration, and we're going to use this equation here to figure out our hydronium ion concentration. Our hydronium ion concentration, this is just rearranging the equation, is our Kw, which is 1 times 10 to the negative 14. This is the same thing. Divided by hydroxide. Then we plug in our numbers, and you end up with a hydronium ion concentration of 1 times 10 to the negative 12. Then you have to compare your hydronium ion concentration with your hydroxide ion concentration. In this case, our hydroxide ion concentration is greater than our hydronium, so this solution is basic. All right, now let's get to the pH scale. I'm going to move this up so we can look at it a little bit easier. All right, pH scale. pH scale runs from 0 to 14. Be careful with that. It is 0 to 14. Less than 7 is considered an acid. Greater than 7 is considered a base, with 7, exactly at 7, being neutral. Now, if we deal with the same concentration of acids, so let's say we're dealing with 1 molar solutions, what we would end up finding is that our strong acids, those that ionize more, end up on this end of the scale, and our weak acids might be here at like 4 or 5. Again, considering that they are all at the same concentration, because I can make things a little more acidic by dealing with concentration. Our strong bases would be at the other extreme end of the pH scale, so they're around 13 and 14, and our weak bases would be somewhere around 8 or 9. Now, I'm going to put on the same scale your hydronium ion concentration. If the hydronium ion concentration is 1, we have a pH of 0. If the hydronium ion concentration is 1 times 10 to the negative 7, our pH is 7. And if it is a base, then our pH, or if it's 1 times 10 to the negative 14, then it is a pH of 14. You should notice that these numbers match. And that's exactly what pH is. pH is the power of the hydrogen ion. I say that's what it stands for. So pH is the power of the hydrogen ion, and it is measured on a logarithmic scale. So it goes by powers of 10. So if you go from a pH of 7 to a pH of 8, it has not increased one increment in its hydrogen ion concentration, but a power of 10. And that's important. So if we look at this, what is the pH of a solution with the hydronium ion concentration of 1 times 10 to the negative 5? Well, we don't even need a formula for this one because pH is the power of the hydrogen ions. And remember that hydronium is just hydrogen bonded to water, so we can take that as the same thing. So the pH of this solution is going to be the power of that hydrogen ion, which is going to be 5. Now, I'm going to write these with the correct number of sig figs, and I'll go into the correct way to do sig figs here in just a moment. But that's the pH. Now, that works every single time as long as this first number right here is 1. If that number is something different than 1, our pH is still going to be close to 5. It's just going to be a little bit lower, a little more acidic. So we have a formula to work with that one. Our pH is equal to negative log of the hydronium ion concentration. Now remember, hydronium is the same thing as hydrogen, so you could see it as negative log of hydrogen ion concentration. So if I have, calculator here, if I have a hydronium ion concentration of 2.3 times 10 to the negative 9 molar, and I want to know what the pH is, then I'm just going to plug that into my calculator. So you've got to hit the negative button, not the subtract, but negative, then hit the log button, and then you're going to type in 2.3 E, or your EE button, negative 9, and I end up with 8.64 as my pH. So this solution, because it's above 7, would be basic. If I had a, let's try another one, hydronium ion concentration of 7.13 times 10 to the negative 3, and want to calculate my pH, again, it's just going to be negative log of 7.31, negative 3, and I end up with a pH of 2.147. So this solution would be acidic because it is lower than 7. And that's how you work with pH. Now, that only involves the hydronium ion concentration. If we are given the hydroxide ion concentration, we can use the formula that we started with in this video cast and figure out our hydronium and then work through that. Or, since we have already gone to this power of the hydrogen ions here for pH, we also have this concept of POH, and it is just the negative log of the hydroxide ions. But nobody really does anything with POH, so we can automatically convert it by subtracting it from 14, because pH and POH are equal to 14. And that comes from that equation that we started with the 1 times 10 to the negative 14 equals hydronium times hydroxide. The way we use this equation right here, and all of these equations that are in rectangles are in your reference table, so you will have access to those. 14 minus POH will give you pH, and so you can move back and forth between pH and POH using the number 14. So let's practice some with that. I've got my hydroxide ion concentration, and I'm going to say that it is 2.4 times 10 to the negative 11 molar. In order to find, and the question is asking for the pH. In order to find the pH, I first have got to find the POH. And I do that using this formula right here, we're going to take the negative log, in the same way we were finding pH before, 2.4 E negative 11, and I end up with a pOH of 10.62. But the question didn't ask for pOH, it asked for pH. So to find pH, what I have to do is use this equation right here. 14 minus pOH will give me my pH. And so I say 14 minus 10.62. 14 minus, and I get 3.38 as my pH, and that would be my answer. And the solution would be acidic because it is less than 7. The hardest part is really just making sure that you read the problem correctly and make sure you know whether they're giving you hydroxide or hydronium. If it's just hydronium, all you have to do is take the negative log of that number. If it is hydroxide, then you find the pOH and then subtract that answer from 14 to get your pH. So, if we have a hydroxide ion concentration of 1 times 10 to the negative 3, what is the pH? Well, again, pOH is the power of the hydroxide ions. So my pOH is going to be 3. And so my pH will be 14 minus 3, which will end up being 11, will be my pH of this solution. And so I end up with having a basic solution there. All right, now it seems that I've done something weird with sig figs here, and pH does have its own special rules. The reason for that is because it ended up being a safety concern. I'm going to move this up just a little bit. If we have something with if it didn't have special sig fig rules, and I had something that had a pH or a hydronium ion concentration of 1 times 10 to the negative 14 molar, my pH, because pH is power of the hydrogen, would be 14. But if it followed regular sig fig rules, I only have one sig fig here. So I would not be able to write it as 14. And a pH of 14 is a very, very dangerous. It will turn your finger into soap if you were to put your finger in that solution. And if I only had one sig fig, I could only write that pH as 10 if it followed regular sig fig rules. Now that is the pH of soap, which is not harmful to you. So as part of a safety concern, what we've decided to do is with pH, these sig figs are always located after the decimal. So the answer to this one, the pH would be equal to 14.0. That is my 1 sig fig after the decimal for pH. And I have some other examples right there. All right, now, if we know our pH and they want to know our hydronium ion concentration, let's say we have a pH of 5.13, and they want to know our hydronium ion concentration. Well, we just have to take our equations that we were working with and rearrange them. But because they're dealing with logs, it gets a little more complex. So what they have done to help you out with that, and it really is to help you out, is they went ahead and rearranged the formulas for you. Now, you're going to have to take the antilog, and that's usually the second function of the log key on your calculator. It should say 10x. And so here are your two formulas. So if I'm looking for hydronium ion, that means I need to use this equation, hydronium ion equals. And I'm going to type it into my calculator, and I'm going to say minus second log, so I get 10 up caret parentheses. You do have to put that negative sign in there, so don't forget about the negative. And I'm going to put in my pH. My pH over here was 5.13, so 5.13. And then I need to put that in scientific notation. You should be able to move that around pretty well. So my hydronium ion concentration would be 7.4. I need 2 sig figs because that's how many are to the right of the decimal, times 10 to the negative 6 molar. Again, if it is square brackets equals, it is always molarity units at the end. I can also do the same thing with hydroxide. Now, if we are looking for the hydroxide ion concentration, we also have a formula for that. But notice it does not involve pH, it involves pOH. So, if I had a pH of that 5.13 and they wanted to know what my hydroxide ion concentration is, the first thing that I would need to find is my pOH. To find pOH, remember pH and pOH are related by the number 14. So 14 minus pH equals, so 14 minus 5.13 is going to be 8.87. That is my pOH. Now I can plug that into the formula, and so again it is second log, or at least it is for me, and then hit that negative button, 8.87, and I end up with a hydroxide ion concentration of 1.3, that's all I need, 2 sig figs, because there were 2 after the decimal, times 10 to the negative 9 molar. Again, square brackets, the answer should be in molarity. So that's how you work with these. See, you're struggling with sig figs, that's okay. We're going to have plenty of practice with it, but it's just something to keep in mind as you're going through.